This video will show you how to do an isothermal precipitation calculation for the formation of aluminum-3 scandium in an aluminum-scandium alloy at 350 degrees using the precipitation module TC Prisma. The end of the video also shows you how to use the precipitation module to model yield strength, which was added to TC Prisma in the 2020B release. This is the first mechanical property to be added to the module. This calculation uses a binary system, so all users, including those who do not have a license for the precipitation module, can still complete the calculation. The calculation is based on Precipitation Module Example 1, which can be accessed from within ThermoCalc in the Help menu, Open Examples, Precipitation Module TC Prisma. To begin, click on the Precipitation Simulation template to get all the nodes we need for the precipitation calculation. Set the database package to Demo, Aluminum-Based Alloy. This will load both the thermodynamic and kinetic aluminum databases. Select the elements aluminum and scandium and set scandium to 0.18 mole%. Our system is now defined, but before we start the precipitation calculation, I'll do a quick one-axis calculation to find the phases present around 350 degrees. Right-click on the System Definer, highlight Create New Successor, and select Equilibrium Calculator. Set the temperature to 300 degrees Celsius, then select One Axis under the calculation type. This calculation type used to be called Property Diagram, so if you have ThermoCalc 2019A or older, select Property Diagram. The calculations will be the same, only the name has changed. We're looking for the phases present around 350 degrees, so set the range from 300 to 700 degrees to capture the temperature we want. Our system is now defined, so right-click on the Equilibrium Calculator node, highlight Create New Successor, and select Plot Renderer. Right-click on the Plot Renderer node and select Perform Now. Once the calculation is complete, a plot will appear in the results pane. We are looking for the phases around 350 degrees, so zoom in around this temperature to get a better view. We can see that there are two phases present at 350 degrees. FCC A1 makes up more than 99% of the system. The remaining part of the system is made up by aluminum-3 scandium, which is the precipitate phase in the alloy we're considering. Remember these two phases because we'll use them in our precipitation calculation. We are now done with our one-axis calculation, so click on the Precipitation Calculator node to begin our precipitation calculation. Notice that our composition carried down from the System Definer. Under Matrix Phase, select FCC A1. Note that if you do not see any phases listed here, it is probably because you do not have a kinetic database selected. If so, simply go back to the System Definer and add a kinetic database. Next, we'll set our precipitate phase to aluminum-3 scandium because that is the other phase present around 350 degrees. We will accept the default settings of homogeneous nucleation in the bulk and interfacial energy estimated by the program. You could choose to define your own interfacial energy settings if you have them. Under Calculation Type, make sure Isothermal is selected, then set the temperature to 350 degrees and set the time to 1e⁷, which is 10 million seconds. Finally, click on the Plot Renderer node and change the axis type to Logarithmic 10 so we get a better view of the plot. Then click Perform at the bottom center of the program. Once the calculation is complete, your plot will appear in the results pane. This plot shows us the mean radius of the aluminum-3 scandium precipitate as a function of time. We can see that at the beginning, the mean radius is quite small and then grows rapidly over time. This new module makes it easy to look at a variety of variables. Simply click on the Axis Variable tab to see what is available. I'll select number density. This calculator also allows you to add additional variables to the same plot so you can compare the results. Simply click the green plus sign to add a variable. Let's select nucleation rate, then click Perform again. The precipitation calculator makes it quick and easy to make changes and replot results, so your plot should reappear almost instantly. Our plot now has two y-axes, one for each variable. We can see that nucleation makes the number of particles increase. At a later time, we reach the coarsening stage where the smallest particles shrink and the total number of particles decreases. The integrated precipitation calculator also makes it easy to add additional plots. Simply right-click on the precipitation calculator, highlight Create New Successor, and select Plot Renderer. Let's look at size distribution this time. Notice that final simulation time, 1e⁷, auto-populates. It's also easy to show the size distribution for several times. Simply enter the times in the time field and separate them with either a space or a comma. I'll enter 5, 10, 100, 1,000, and 100,000, and I'll leave 1e⁷. Change the axis type to logarithmic 10 again, then click Perform. All the size distributions show us that as nucleation is occurring, the size distribution grows. But when we reach coarsening, the height of the size distribution decreases. Finally, if you're using the example file to run this calculation, you'll see the experimental results in the plot. We can see that they have fairly good agreement to our calculation, but it is not perfect. This can be improved by changing the interfacial energy rate. The newly integrated precipitation calculator makes it easy for us to do this through cloning, which allows us to keep our first simulation and create an identical copy that we can make changes to and compare to the original. Right-click on the precipitation calculator node and select Clone. You can also clone the entire tree, but we only need one node, which will connect to the existing plot renderer to compare the two sets of results. I'll change the name of this new calculator so that we don't confuse the two. To do this, right-click on the calculator, select Rename, then rename it to Sigma Prefector 0.8. Then click OK. Now change the interfacial energy to a prefector of 0.8. Next, we need to link the plot renderer to the second calculator so that we can directly compare the two. Right-click on the plot renderer node, highlight Add Predecessor, and select Sigma Prefector 0.8. Notice that the plot renderer is now linked to both precipitation calculators. Make sure that the axis type is set to logarithmic 10 under both axes. Then select the tab for the second calculator and change the axis type to logarithmic 10 under both axes there as well. Then select Perform. Once the plot is updated, we can see that the average radius is similar in both calculations, but there's better agreement with the experimental results at a prefector of 0.8. Lastly, we will use the results of the precipitation simulation as input for a yield strength model. The yield strength model used in the precipitation module is the same as the one from the property model calculator. To set up the model, right-click on the precipitation calculator node and select Create New Successor, Plot Renderer. Set the y-axis variable to yield strength. When you select this, a configuration panel becomes available, which is the same as the panel in the property model calculator. Here you can select the precipitation strengthening model, set the parameters, and so on. I'll set the precipitation strengthening model to aluminum base. Change the axis type to logarithmic 10, and then click Perform again. The program will use the results from our precipitation simulation as the input for the yield strength model. Once the calculation is complete, a plot will appear which shows the yield strength as a function of time. If you are running the example file, you will also see the experimental data, which shows good agreement to our results. We hope you found this video useful. We have many other videos available on our website at www.thermocalc.com.